Okay, sorry about the unexpected video notes for today, but due to the snow day, we've got to start Chapter 5 with this video. So Chapter 5 is all about analytical trigonometry, and the first couple sections are all about using identities, basically to rewrite problems. So we're just going to start out with a little bit of review. It says use the given values to evaluate, if possible, the remaining trig functions. So let's see what we can glean from this information. If we know this statement, this should tell us about its cofunction. Notice that we have this pi over 2 minus theta. That essentially is telling us that the secant of theta is 3, that its cofunction is going to be 3. So really this is giving us 2 of the 3 values. And so this is basically saying that, all right, if we know that the sine is 2 root 2 over 3, then what we can do is very easily find, for example, the cosecant is going to be 3 over 2 root 2. And if we rationalize that, that gives us 3 root 2 over 4. We know then that if the secant, like we said here, is 3, then we know that the cosine, of theta is going to be its reciprocal, which is 1/3. And we know that the tangent theta is sine over cosine. And notice that the denominators will cancel out, so that means that the tangent theta is going to be 2 root 2. And that the cotangent theta will be 1 over 2 root 2. And if we rationalize that, that gives us root 2 over 4. So here we're able to find then all of the trigonometric functions. Okay? What if the cotangent of theta is 5/6? We know that that is going to be possible in either quadrant 1 or quadrant 3. But since cosine has to be less than 0, we know that this triangle must be living in quadrant 3. And we know that cotangent is x over y. And because it lives in quadrant 3, I'm going to label that as -5 and -6. So I can use the idea of x squared plus y squared equals r squared. And I find 25 plus 36 equals r squared. So I know that r squared is 61, and that r then is root 61. So now that I have that information, I can find the other trig functions. The sine of theta then, so again, our x essentially is the -5, the y is the -6. So the sine is going to be y over r, so -6 over root 61, which ends up being -6 root 61 over 6. We know the cosine is going to be x over r, so 5 over root 61, and when we rationalize 5 root 61 over 61, the tangent of theta we know is the reciprocal of cotangent, so that's just going to be positive 6/5. And then the cosecant of theta is going to be r over y, so that's just negative root 61 over 6. We know that the secant of theta is going to be r over x, so negative root 61 over 5. And they told us the cotangent theta. I'm just going to write it because I want it to be even on both sides of issues. And so then that's our 6 trig functions. Likewise, if tangent theta is undefined, we know that tangent theta is undefined at pi over 2 and 3 pi over 2, but it says that the sine is positive, so that tells us it's going to have to be up here at pi over 2. And essentially the ordered pair at that point is 0, 1, if we're thinking about the unit circle where r is 1. So in that case, we know that the sine of theta is going to be 1. The cosine theta will be 0. The tangent theta is going to be undefined. Oops, I don't want the equals, like we stated. And so then we know the cosecant theta is 1 also. They still have bells on snow days. The secant theta, is then going to be undefined, and the cotangent of theta will be 0. So again, just a little review of these different evaluation of the different trig functions. It follows down here just some good definitions to know, but the one that I want to really focus on for this section is the idea of an identity. An identity is a statement that is always true for all values of the variable within its domain. And this talks to you a little bit about how if you have a simple linear equation, that's true. However, when we start getting into these rational equations, it's only true, for example, for values that are not 1 or negative 1, because you want to make sure that the values fit the domain. Okay, so what we're going to do is use trig identities from chapter 4, like the reciprocal identities, the Pythagorean identities, cofunction identities, and even on identities, to find the values of trig functions and to simplify expressions. So here's a problem. It says, use the fundamental identities to simplify the expression. Okay. And always, when we reduce, we're assuming the domain is taken into consideration, even though we're not writing it. So we have secant x minus tangent x sine x, and we want to just try to simplify that somehow, right? Well, one thing that we could do is write this in terms of sine and cosine. That's one of a little trick that we'll be using in these sections. And if we did that, secant x would be 1 over cosine x. Tangent x would be sine of x over cosine x. And then we have sine of x. So we use the reciprocal identity here, and we used the, well, we know that tangent is sine of x over cosine of x. I forget what that one's called. But anyway, so we know that. And look what happens here is that we can think about writing that over a common denominator. We can really change this into 1 minus sine squared x over cosine x. Notice that if we would have rewritten this, we could have rewritten that as sine squared x over cosine x. And again, now that we have those same denominators, we could rewrite that as 1 minus sine squared x over that common denominator of cosine x. And we know that the Pythagorean identities, just a little reminder that one of our Pythagorean identities is that sine squared x plus cosine squared x equals 1. So notice that 1 minus sine squared x is cosine squared x. And when we do these problems, you guys, you're going to get so good at rearranging those Pythagorean identities. So anyway, we can rewrite the 1 minus sine squared x as cosine squared x. And now cosine squared x over cosine x is just going to be cosine x. And that's pretty simple, right? And so how fun is that we turn the secant x minus tangent x sine x just into cosine x just by using identities. Okay? Let's try number 5. We have sine squared x times cosecant squared x minus 1. Well, another one of those Pythagorean identities is that cotangent squared x plus 1 equals cosecant squared x. So once again, you can see that if you manipulate this around a little bit, that cosecant squared x minus 1 is the same as cotangent squared x. So let's maybe do that. Let's rewrite that cosecant squared x as cotangent squared x. Now that we've got that simplified, again, another tactic that we used in number 4 is to write things in terms of sine and cosine. And we know that cotangent squared x would be cosine squared x over sine squared x. And we can cancel these out, and here we're left with cosine squared x. Okay? And so what we would do in these problems is we would, all right, so in a test situation, it would be like a matching thing, or we would say, write this in terms of sine x, or write this in terms of cosine x, so you kind of have an idea of where to go. But notice these problems, it was pretty self-explanatory when you got to the end that that's probably as simple as it's going to be. Let's try number 6. We have tangent squared y over secant y plus 1 plus 1. I'm looking at this and you got to brainstorm how can I manipulate different pieces. And one thing that I noticed is that another one of our properties is that tangent squared y plus 1 equals secant square y. And I just chose y because they're talking about y here. So notice that this is tangent squared y, and I could rewrite that as secant squared y minus 1. And the reason I might think about that is because this denominator involves secant y, and so at least I'm getting everything in terms of the same trig function, right? So let me rewrite that tangent squared y as secant squared y minus 1. And now over here, I can just then rewrite the rest of the problem. So secant squared y minus 1 over secant y plus 1, and then plus 1. Well, isn't this factorable? This is the difference of squares. So I can make this secant y plus 1 times secant y minus 1. And then that can all be over secant y plus 1. And then I have this plus 1 here also. And notice that when I factored, I can cancel. I can cancel these out. And I'm just left with secant y minus 1. And then I have this guy plus 1. Well, and the negative 1 and 1 cancel, and I'm just left with secant y. There we go. See, these are so fun. All right, number 7. We have cosine squared x over 1 minus sine x plus cosine squared x over 1 plus sine x. There are a couple ways that you can do this one. One thing that you can do is make a common denominator with the fractions. I think we'll practice that in a different one. So let's just keep playing with these Pythagorean identities. I think that's my favorite thing. And we can use that idea of the cosine squared x. So we said up here that another way to write cosine squared x was 1 minus sine squared x. So maybe we could do that here. So in place of these cosine squared x's, I can have 1 minus sine squared x. So I can just replace those. And like we did in number 6, notice that this is really now a difference of squares. So I can factor that. Each of those difference of squares. And now that I've factored with the difference of squares, I see that I can cancel some things out. So I have the 1 minus sine x that can cancel here, and the 1 plus sine x that can cancel here. So I have 1 plus sine x left, and then here I have 1 minus sine x left. And then look here, this sine x and negative sine x cancel. And I'm left with 1 plus 1, which is 2. So I just think these are so cool that like this is equal to 2. Who knew? But those are the kind of things that you guys are going to be doing in this lesson. And to be honest, through all of 5.1 and 5.2. So I'm not going to read these two in the video, but basically like these are some things that we're going to be practicing throughout. So you guys can kind of use this as hints. But again, us practicing together is going to be, I think, the best way for us to get better at these. Okay, so let's do a couple more. Oh, do I want to do all of these? Okay, let's do 8. So one thing that you could do, again, one trick is to turn everything into terms of sine and cosine. So we have this cotangent. So we're going to, in these problems, we're going to get one side equal to the other. And you can't use both sides. Like you use one side and you try to make it equal to the other. You can start with either the left or the right. But you usually start with the most complicated side and try to get it down to the least complicated side. So you're going to work with one side. So that's the thing. And we'll, again, keep practicing this. You're going to work one side only. And then get it equal to the other side. And we'll talk about then how to write all that out. Okay? So this, I believe, is the more complicated side. So let's put everything in terms of sine and cosine. So cotangent theta is going to be cosine theta over sine theta. And cosecant theta, we know, is 1 over sine theta. So essentially, I took this side and I'm working on that left-hand side. Well, one thing that I could do is I could, to simplify this, you could either multiply by sine theta over sine theta, or another thing you could do is you could take this and multiply by the reciprocal. Either way, what's going to happen is you're going to be left with cosine theta over 1, which is just cosine theta. Now, notice that we've gotten to the other side that we wanted. So then I want you then to say equals cosine theta, and then you're going to put like a smiley face or a check or something, and that's verifying the identity. The problem's telling you this. You are working one side to say, yes, indeed, this cotangent theta over cosecant theta is equal to cosine theta. Okay, so this last step will always be that, basically an identity statement. Okay, we'll try number 9. Usually addition is more complicated than multiplication. So let's try to use maybe that same thing that we just did here. We could rewrite in terms of sine and cosine. So tangent x is sine of x over cosine x, and cotangent x is cosine of x over sine of x. And something that often helps us out is if we get common denominators. And so to create the common denominator, I would have to multiply this by sine of x over sine of x. And I'd have to multiply this by cosine of x over cosine of x. And hopefully you guys see that you will end up with a common denominator of cosine x sine x. Okay. And then here, if I take sine of x times sine of x, that would give me sine squared x. Cosine x times cosine x would be cosine squared x. So I have, in creating one denominator, I have sine squared x plus cosine squared x over cosine x sine x. Oh my gosh, look, this is one of those Pythagorean identities. So we know that sine squared x over, plus cosine squared x is 1. So that means I have 1 over cosine x sine x. Now I want to remind you guys that when you're multiplying, you can kind of split it into 2 different factors here. So this is really the same as 1 over cosine x times 1 over sine x. And why would I do that? Because what's 1 over cosine x? It's secant x. And what's 1 over sine x? It's cosecant x. And that means that now I verified this identity. And then again, you can put put a smiley face or a check or whatever to say that, yep, we have verified that identity. We have shown that tangent x plus cotangent x is equal to secant x cosecant x. Okay. Okay, I'll work through 10. In number 10, we have this identity, and to me, this one looks a little more complicated than this side. There are a couple ways to do this one. It's just hard to decide because it's all so fun. Okay, I'll give you one tactic. So in addition to factoring, another thing is that, do you see that these are all over one denominator? One tactic, and I have another tactic online if you want to look on that one on the filled in notes. One thing that you could potentially do is to divide each term in the numerator by the denominator. We haven't done that, so we'll do that here. Okay. And what happens is then this turns into cosine squared theta. This turns into -1. And what's sine theta over cosine theta? Why, it's tangent theta. And look how close we are already. We've got the tangent theta part. We just want to turn this into negative sine theta somehow. But how could we do that? Well, you guys need to make sure that you can manipulate that. Remember that we know that sine squared theta plus cosine squared theta equals 1, right? So if we had cosine squared theta minus 1, do you see that that does equal the opposite of sine squared theta? So I know then that this is negative sine squared theta plus tangent theta. And that's essentially equal to this, right? Just so it's super pretty, I'm going to just rewrite it real quick as tangent theta minus sine squared theta. Yes, indeed, that does equal tangent theta minus sine squared theta. Okay? So again, there's a different way that you could do it also on the filled in notes online, but I think this way is actually a little shorter. Okay, so number 11. Last one, we've got tangent theta over 1 plus secant theta plus 1 plus secant theta over tangent theta. We want to turn that into 2 cosecant theta. Well, this clearly looks like the more complicated side, so let's maybe do that. And one thing we can do is create common denominators. So essentially, to create the common denominator, I'm going to have to multiply this guy by tangent theta over tangent theta. And I'm going to have to multiply this guy by 1 plus secant theta over 1 plus secant theta. And so, again, we'll have the common denominator of 1 plus secant theta times tangent theta. Okay. And let's see what each of these terms became. So tangent theta times tangent theta would become tangent squared theta. And then we have 1 plus secant theta times 1 plus secant theta. I don't know. You probably could FOIL that out in your head, but I'll just in case, I'll write that out. So then here we have 1 plus secant theta squared. So again, let's multiply what that is out. We know that 1 plus secant theta squared is going to be 1 plus 2 secant theta plus secant squared theta, and then all over 1 plus secant theta tangent theta. So one other thing is that I see a lot of secant thetas, and this tangent theta seems to be the one at this moment that doesn't really fit. But remember that there is that Pythagorean identity that tangent theta squared, tangent squared theta plus 1 equals secant squared theta. So isn't this really a secant squared theta? So this is really secant squared theta plus 2 secant theta plus secant squared theta over that common denominator that we had. And eventually you can combine some of these steps, but especially at first, I'm just trying to show you everything. Then we can combine these like terms, right? Secant squared theta plus secant squared theta is 2 secant squared theta over that common denominator. So I have 2 secant squared theta plus 2 secant theta over the common denominator. Notice I have a common factor here of 2 secant theta. So you can factor out that GCF to get secant theta plus 1 times 2 secant theta over the common denominator. And look, these cancel. And so I'm left with 2 secant theta over tangent theta. So another thing that you could do is that if you know that you have 2 secant theta over tangent theta, isn't that the same, if you have 1 over tangent theta, isn't that the same as cotangent theta? So from here to here, I'm keeping the 2 secant theta, but instead of writing it over tangent theta, I'm writing the 1 over tangent theta using the reciprocal identity. Oh my gosh, can you not see this? I'm so sorry. 1 over tangent theta as the reciprocal identity of that cotangent theta. And now if you think about things in terms of sine and cosine, secant theta is 1 over cosine theta. cotangent theta is cosine theta over sine theta, and you can see that these cancel. And so essentially I'm left with 2 times 1 over the sine of theta, which is 2 cosecant theta. And that's what we wanted, equals 2 cosecant theta. Yay. Okay? So that's kind of the scoop. This is what we're going to be doing for the next couple days, a lot of these identities. So the identity ones that tell you where you're going are nice because it kind of gives you an endpoint to go to. But just do your best on these that don't have an endpoint. In a test situation, it should be pretty clear. Okay? All right, and we'll keep practicing when I see you next. Okay? Good luck. Have a good day.